We will start by learning the proper names of the component parts. When you use the names of the components, it instills confidence in your workmanship, as well as helping you to communicate with a coworker, employees, or perhaps a customer. The machine base and column is the foundation of the milling machine. This heavy casting is the main structural member that provides the components with strength and resistance to vibration. The knee positions the table and the workpiece along the Z-axis under the spindle. This provides for a variety of workpiece sizes and lengths of tooling. Make sure that when taking heavy cuts, that the travel locks are enabled to aid with rigidity. The saddle carries the table along the Y-axis. Because the Y-axis has about half the travel as the X-axis, make sure that the length of cut has been taken into consideration, and remember to use the travel lock when taking heavy cuts. The table provides the left and right X-axis motion. This axis often has a power feed option that consists of a motor and variable feed settings. The table also has T-slots available for a variety of clamping. T-slots also provide coolant to flow back into the coolant tank, which is usually located in the casting base. Make sure you take advantage of the travel locks located on the saddle. Adding to the versatility of the mill, the turret enables the head assembly to rotate 360 degrees. The ram enables the head assembly to move forward and backwards, controlling the throat depth. When working on large parts, notice how the Y-axis can be limited. Also, the X-axis can only span the table's amount of travel. Only a small section of the part can be machined. However, the ram and the turret expand the work area, so that most of the part is available for machine work. The head assembly is the heart of the milling machine. It houses the motor, the spindle, and the spindle bearings, as well as the gears and pulleys. The head is able to pivot on two different axes. One sweeps front to back and the other sweeps left to right. We will go over how to bring these axes into perpendicularity with the X and Y axes in a later lesson. The head also houses the quill, which travels along the Z-axis. Since the quill gets its stability from the head, make sure that when performing side-load cutting operations that the quill is raised and locked. The digital readout usually measures the X and Y axes. Take time to get familiar with this time-saving device. The lube system here, when pulled, lubes all the ways and lead screws. The components in the head assembly will require different methods of application. Always consult the manual for type of lube and frequency of application. The forward and reverse switch enable the spindle's rotation at a given RPM in either clockwise or counterclockwise rotation. The first step to setting up a part would be to consider the print. Since the part is made from bar stock, a vise will work well for holding it. Before setting up the part, the machine should be checked to make sure all bolts are tight and calibrated so that it's accurate. The first part we will calibrate is the vise. Make sure the vise jaws are parallel with the x-axis. So if the vise is rotated off angle, even if the first feature was positioned in the right location, all the following features will follow the x-axis, not the vise jaws. The second feature of the mill to calibrate would be the head. It needs to be perpendicular with both the x and y axes. One way to accomplish this would be to consult the angular scales located on the back of the head assembly. Now that the mill is prepared, let's decide on the order of operations and the required tooling. We will need a list of each. Our first operation will be to mill one side of the part for our X0 location. Our second would be to pre-drill the slots and the hole in the center. Taking into consideration the radius is 1/4 inch, we will need to drill a bit smaller, leaving room for a finish cut. Third, we will mill the slots and finish the hole in the center with a 1/2 inch end mill. And to consolidate tooling, we will also use the end mill to mill the side for 0. Now, when clamping the material in the vise, make sure the vise, parallels, and workpiece are free from chips and debris. Because one side of the material will be machined, a fraction of the workpiece should extend away from the vise. The first operation requires a 1/2 inch end mill. It will need to be properly set in the spindle. The 4 steps to accomplish this are to apply the brake, loosen the drawbar about 3 or 4 rotations, then tap on the drawbar to break the taper lock. Note, this will free the tool, so prepare to catch it if it were to slide from the collet. Continue turning the drawbar until the collet is completely removed. Now examine the collet. Notice the groove or guide here. This lines up with a keyway in the spindle. The keyway is not designed to bear any force. It is designed to keep the collet from rotating when inserting or removing the collet. After the collet has been drawn into the taper, the collet collapses onto the tool, and this is what resists the cutting torque. If the keyway was ever sheared, it would make for a severe inconvenience. Always make sure the drawbar is tight before use. The first cut will enable the setting of 0 for the x-axis. In this case, the print will determine the location of x0. In this way, the math from print to part will be kept simple. There will be as little adding and subtracting to find locations relative to different positions. This print in particular uses the baseline dimensioning system for the machine's x-axis. So the baseline is the best place to set the 0 location for the x-axis. When turning on the spindle, make sure that the end mill is rotating clockwise. Also, that the cutter is pushing against the material during the cutting operation. If the cutter is positioned in a way that will allow it to pull the workpiece, it could pull the table and overload the cutter. Either the cutter will break or the material will move in the vise. Both of these situations could cause flying debris and a severe hazard. Before moving the x-axis, set the digital readout to 0. Then divide the diameter in half to get the radius. Since we have a 1/2 inch end mill, our radius would be 1/4 inch. Now move the table 1/4 inch toward the tool. Then zero out the readout for the last time. The center of the spindle is now lined up with the edge of the part. Setting the location for the y-axis will call for a different method based on the same principles. Again, let the print determine the best location for y0. Since all the features lie on the same y location, it should make sense to let that be our y0. When setting the y location, make sure the spindle is off and in the neutral position. This allows the spindle to be rotated freely until the end mill brushes the workpiece. Zero the readout for the y-axis, lift the quill, and move the part toward the tool the amount equal to the end mill's radius. Again, reset the readout to 0. Then divide the width of the bar stock in half and move the table toward the tool that amount. The spindle is now centered over the middle of the part. Now zero out the readout for the last time. Our part has been successfully set up. Let's move to our cutting operations. Now that the part is held in the vise and the zero location is set, consider the print and visualize the remaining steps. The next step in the order of operations is to pre-drill the slots and the hole with a 31/64 drill. This leaves material for the end mill to perform a cleanup pass. When taking the locations from print to the machine, keep in mind the X and Y zero locations. What effect will the zero locations have on the numeric values for the hole positions? To find the answer, we need to consider the coordinate system. Since we set the x0 on the right side of the part, all the numbers will be descending from right to left, so all the features will be represented by negative numbers. It might be beneficial to list the hole positions on a chart in the order they will be machined for quick reference. In this case, just chart the negative x values, because all the y locations lie on the 0 location. The next operation requires the 31/64 drill. A drill chuck has been installed. Make sure that the drill has been tightened thoroughly before use, otherwise it could slip and damage both the drill and the chuck. Now position the drill at the first coordinate and engage the spindle at 600 RPMs. During drilling operations, there is never a need to apply more force than the quill lever will allow. Nor will there be a need to use two hands and force it with your body weight. If it seems not to be cutting, consider the drill's rotation, that it's going clockwise, and the drill's cutting edge. You may also want to consider the material's hardness. Continue drilling the holes at the given positions. The next operation requires the half-inch end mill. If the end mill is installed in the drill chuck, because the end mill is not supported at every angle, the 3-piece clamping system will allow the piece to move and flex during side load operations. Also, it can make it spin off center. Therefore, the collet is ideal because the shank is supported at all angles and is inside the spindle. That makes this setup very rigid. If the quill is extended to reach the work, this could cause the quill to flex. Notice the exaggeration here. Make sure that the quill is raised in the head and that the knee is moved to make up for the difference. In the current setup, the y-axis should be locked for rigidity. Now engage the spindle at 600 RPMs and position the tool for the current operation. When the tool is at the final depth, lock the quill. The end mill should pass completely through the workpiece. As the table is fed to the next position, make sure not to pass the coordinate. Unlock the quill and use the end mill for a reamer for the hole in the center. If the part had a tight tolerance, this operation would require a reamer mounted in a drill chuck or collet. After the part is completed, clean up the machine and leave it in good condition for the next user.